Okay, now we talk about the other process, charging process, which is of conductors in particular, which is charging by induction. We have already discussed quickly the charging by rubbing. Here we talk about charging by inductions. Now, assume that we start with a neutral metallic sphere. This is the metallic sphere, and as you can see, it has the same amount of electrons and protons because it's neutral. Okay? And you want to charge this sphere, metallic sphere, by induction. What we do when we want to charge it by induction is that we bring a negatively charged object. For example, assume that I bring a negatively charged object. In this case, it can be a plastic rod which is rubbed and made to have a negative charge. Now, you bring it close, but not in contact with this metallic sphere. Okay? Now, this is a conductor. Since it's a conductor, the electrons here are free to move through that material. So when this comes close, it will repel the electrons that were here. Remember? The electrons were uniformly distributed over the whole material when it was neutral, and the same applies for the protons. Now, when you bring this in, it will repel these electrons, and these electrons will run away, okay, and will appear here. However, so we have like a sort of positive charge will appear here and a negative charge will appear here. But this is not a permanent charge, because once you remove this, okay, these electrons will redistribute themselves and the object will be again neutral without, you know, partial charge appearing here or positive charge appearing here and negative charge appearing here. This type of charge, we call it bound charge, because this charge is there as far as this inducer is there. Once you remove this, this charge disappears. So this is called bound charge. Now, but we don't want this. We want to have this object carry a permanent charge. So what we do, we ground it. We ground this sphere while this is still there. Okay? What do I mean by grounding? By grounding, I mean I attach a conducting wire to the ground. Now, you can think of the ground, or the earth, sometimes call it earthing. You can think of it as an infinite source and sink of negative charge of electrons. So this means that you can send as many electrons as you like to the earth, and it will take it, and you can receive, if you need, as many electrons as you like from the earth, and you can get that number. Okay? So this is what grounding achieves. So when you ground this with this present, then all the excess electrons here, okay, in this region, because now some of them, okay, you have a number equal to more than the number of protons present in this area. So these excess electrons will find their way to the ground, okay, to the sink that you have open to them. Okay, so this is what's going to happen. Now you have a net positive charge appearing on the whole sphere, as you can see, because the excess electrons we have dumped them to the ground. Now, so we have a charge. This charge, however, now is not uniformly distributed. Okay, it is appearing here, but here in this area, we don't have charge. Okay. Now, what you do, we are not done yet. You want to have this charge permanent, and you want to have it distributed over the whole surface uniformly. So what you do, you cut or you remove the grounding while this is still there. What happens if you, let me defer this question to later. So you remove this wire that you had here, while this rod is still there. Okay. Now you have a net positive charge appearing on the sphere, but this charge is not distributed over the whole sphere. It is on the part that is opposing this conductor, this rod, which is negatively charged. Now, so what you do now, if you remove the rod, the negatively charged rod, then there is nothing to repel the electrons and keep them away from this part. So what will happen is that they will redistribute themselves over the whole sphere, and you will have a positive charge now appearing on the whole surface of the sphere. Now, since the sphere is a symmetric object, then that charge will be, the density of that charge will be the same over the whole surface. There is no reason, due to the symmetry, for the charge to be more on one part than it is on the other part, because of the symmetry. Okay, so the charge will be uniformly distributed now over the surface of the sphere. Now, two observations are important here. The first observation is that when we want to charge this with a positive charge, the sphere with a positive charge, we used a negatively charged object. So if you want to charge this with a negative charge, you need to use a positively charged object to induce that charge. Now, try to follow the same steps and see what happens, or how you can charge by induction a neutral sphere with a negative charge by bringing in a positively charged object, like a glass rod, for example. The second thing is that none of the negative charge on the plastic rod has been lost. So that's what has happened here. You brought on that glass, plastic rod. It has some charge on it, but this charge did not get transferred to the sphere. It remains there. Okay, so this is another important observation. Now look at this checkpoint and try to answer it. If you have really understood what we have said, you should be able to answer this. Now, just the last thing that I'd like to discuss is an example that everybody knows, and we used to do that when we were kids, all of us probably, and which is we used to rub a balloon with our cloth, and then when we put it near on the wall, you used to note that this balloon sticks to the wall. Okay, so what's really happening there? We just want to look closer and see what happens in this case. Now, when you rub the balloon, we know somehow that it's losing electrons in this case, and so there is a positive charge appearing on that balloon. Okay, the balloon is a conductor, is an oscillator. Okay, so the charge that appears here stays there at that surface, at that part of the balloon. And when you hold it away, then this charge will not be lost, and so it will remain here for some time. Now, the wall is also an insulator, or the paint on the wall is also an insulator. So what you do is that you bring the balloon and you put it in contact with the wall. Now, this is an insulator, so there are no free electrons. Okay, but the positive charge here will attract the negative electrons from the molecules that are forming the paint. Now, they will not leave their molecules, but what will happen is that somehow each molecule will be polarized with the negative charge, or with the electrons of that molecule coming closer to the balloon, to the surface here. So what we'll have here, we'll have like a positive charge here and a negative charge here. So these attract each other, and once you keep it in touch, then what will happen is that it will get, when you put it, it will be attracted by the electrons in the wall, and it will get stuck to the wall. That's what's happening. Now, as time passes, of course, this charge will be lost because transfer of electrons will take place, and it will neutralize this, and it falls after that. So this is what happens. So this is the balloon phenomenon that everybody knows. This is all about electric charge and charging objects.